Testing, can you hear me? Testing again, can you hear me? Testing one last time. Hello. Okay, so I'm going to be studying introductory statistics again. So last stream I learned about continuous random variables. This stream I'll be learning about the normal distribution. Try to finish this. It doesn't seem to have many chapters. Try to finish this and the central limit theorem. Hold on. The normal a continuous distribution is the most important of all the distributions. It is widely used and even more widely abused. Its graph is bell-shaped. You can see the bell curve in almost all disciplines. Some of these include psychology, business economics, the sciences, nursing, and of course mathematics. The probability density function is rather complicated. Do not memorize it. It is not necessary. So 1 over sigma times 2 pi e to the power of minus half. Okay. The cumulative distribution function is p x less than x. It is calculated either by a calculator or computer. Curve is symmetric about the vertical line drawn through the mean, mu. In theory, the mean is the same as the median because the graph is symmetric about mu. As the notation indicates, the normal distribution depends only on the mean and the standard deviation. Since the area under the curve must equal 1, a change in the standard deviation, sigma, causes a change in the shape of the curve. The curve becomes fatter or skinnier depending on sigma. A change in mu causes the graph to shift left and right. This means there are an infinite number of normal probability distributions. One of special interest is called standard normal distribution. The standard normal distribution is a normal distribution of standardized values across z-scores. Z-score is a measure in units of standard deviation. For example, if the mean of the normal distribution is 5, the standard deviation is 2, the value 11 is 3 standard deviations above the mean. Calculation is as follows. So x, we have mu, we have 3 to 11. So what is this 3 over here? Mean is 5, the standard deviation is 2. Oh, z is what we are calculating. The z score is 3. Okay. So the z score is how far away from x is it? Like how many standard deviations away is x from the mean. That's the z-score, right? The mean for the standard normal distribution is 0. The standard deviation is 1. The transformation z is equal to x minus mu over sigma produces the distribution z normal 0, 1. So it produces a normal curve with mean 0 and standard deviation 1. The value x is given in the given equation comes from a normal distribution with mean mu and a standard deviation sigma. The z-score tells you how many standard deviations the value x is above or below the mean mu. Values of x that are larger than the mean have positive z-scores, and values of x that are smaller than the mean have negative z-scores. If x equals the mean, then x has a z-score of 0. But shouldn't this only be possible if x is the mean? The value of x is the mean value. Suppose x is distributed by a normal curve with mean 5 and standard deviation 6. Oh, wait. This says that x is normally distributed. X is a normally distributed random variable with mean 5, standard deviation 6. Suppose x is 17, then the z-score is 2. This means that 17 is 2 standard deviations above or to the right of the mean 5. Now suppose x is 1, then the z-score is minus 0.67. That means 1 is 6.7, 0.67 standard deviations to the left of the mean. Some doctors believe that a person can lose 5 pounds on the average in a month by reducing their fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Let x equal the amount of weight loss by a person in a month. Use a standard deviation of 2 pounds. X is equal to, so x is normally distributed with mean 5, standard deviation 2. Wait, what is x exactly? The amount of weight lost by a person in a month. So 5 pounds on average in a month by reducing their fat intake and by exercising consistently. Some doctors believe that it should have the curve of uh, 5 pound loss on average and standard deviation of 2. Suppose a person lost 10 pounds in a month. The z-score when x is equal to 10 is z is equal to 2.5. The z-score tells you that x is equal to 10 is 2.5 standard deviations to to the to the right of the mean, which is 5. Suppose a person gained 3 pounds, a negative weight loss. The z is now negative 3. So, wait. Let me just open Desmos as well. So we have here x minus mu minus 3 minus 5 divided by the standard deviation, which is 2. So z-score is minus 4. This z-score tells you that x is equal to minus 3 is 4 standard deviations to the left of the mean. Suppose the random variables x and y have the following normal distributions. X has this, y has this. X is equal to 17, then z is 2. Y is equal to 4, then what is z? Y is distributed with mean 2. So 4 minus 2 divided by 1, which is, so the z-score is 2. The z-score allows us to compare data that are scaled differently. To understand the concept, suppose x is distributed with a normal curve, phi, mean 5, and standard deviation 6. Uh, so suppose this random variable represents weight gains for one group of people who are trying to gain weight in a 6-week period, and y is normally distributed with mean 2. So y measures the same weight gain for a second group of people. Again, a weight gain would be weight loss. Since x is equal to 17 and y is equal to 4 are each standard deviations to the right of their mean, they represent the same standardized weight gain relative to their means. If x is a random variable and has a normal distribution with mean mu and standard deviation sigma, then the empirical rule states the following. About 68% of the x values lie between minus 1 sigma and plus 1 sigma. So 68% of values over here. 95% of values lies between minus 2 and a plus 2. Minus 2 plus 2 covers 95%. 99.7% of the x values lie between minus 3 and plus 3. 3 and plus 3, 99.7. The empirical rule is also known as 68, 95, 99.7. The mean height of 15 to 18-year-old males from Chile from 2009 to 2010 was 170 centimeters with a standard deviation of 6.28 centimeters. Male heights are known to follow a normal distribution. Let x be the height of a 15 to 18-year-old male from Chile in 2009 to 2010. So it follows a normal distribution with a mean 170 and standard deviation of 6.28. The z-score when x is equal to 168 is 170. So wait, 168 minus 170 divided by 6.28 minus 0.3184. So that this z-score tells you that x is equal to 168 is to the left, sorry, is 0.318 standard deviations to the left of the mean, which is 170. And then z is 127. 127 tells you that the male's height is, the z square is 127. So he's really, it's 1.27. So 177.9. So 177.9, sorry, is so 1.27 standard deviations to the right of the mean. What is the male's height? 177.98. The shaded area in the following graph indicates the area to the left of x. This area is represented by the probability px less than x. Okay. The area to the right is then px greater than x is equal to 1 minus px less than x. Remember, px less than x is the area to the left of the vertical line through x. Probabilities are calculated using technology. There are instructions given as necessary for the calculators. Okay. The final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that a randomly selected student scored more than 65 on the exam. Is there any normal distribution over here? Normal, histogram, normal distribution, mean of 63, then standard deviation of 5. Sorry, oh no, mean 63, standard deviation 5. See here, right? Find the probability that a randomly selected student scored more than 65 on the exam. I never used this area. Probability that a randomly selected student scored more than 65. So x is more than or equal to 65, so 0.345. 3446. I've never used this distribution thing before. Um, yeah. Where's was there any other question? Find the probability that a randomly selected student scored less than 85. So less than 85 is 1. How much is it out of? Find the 90th percentile. That is, find the score K that has 90% of the scores below K, 10% of the scores above K. 90th percentile. So I want the probability to be 0.9, right? Find the 90th percentile. Let K be the 90th percentile. The variable K is located on the x-axis. Probability is the area to the left of K. 90th percentile separates the exam scores into those that are same or lower than K and those that are the same or higher. 90% of the test scores are the same or lower than K. 10% are the same and higher. The variable K is often called the critical value. But how can we calculate this K? They didn't tell us that. Unless we use the equation, but What is the equation for finding the thing? Inverse norm, 90th percentile. Personal computer is used for office work, at home, research, communication, personal finances, education, entertainment. Yeah, whatever. Suppose that the average number of hours on a household personal computer is used for entertainment is about 2 hours per day. So the average is 2. Okay. Average is 2. Standard deviation. Assume the times for entertainment are normally distributed and the standard deviation for the times is half an hour. So 30 minutes. So 2 hours and half an hour. Find the probability that a household personal computer is used for entertainment between 1.8 and 2.75. 1.8 and 2.75. 0.589. Okay. And the maximum number of hours per day that the bottom quartile of the household uses a personal computer. So the bottom 25%, right? So we have to use the inverse norm. I wish these ones had answers. These are just, they just seem to be questions. Yeah, but go to the next chapter. Central limit theorem. Uh, why we so concerned with means? Two reasons are they give us a middle ground for comparison. It is easy to calculate. In this chapter, you will study means and the central limit theorem. Central limit theorem is one of the most powerful and useful ideas in all of statistics. There are two alternative forms of the theorem. Both alternatives are concerned with drawing finite samples size n from a population with a known mean mu and a known standard deviation sigma. First alternative says that if we collect samples of size n with a large enough n, calculate each sample's mean, create a histogram of those means, the resulting histogram will tend to have approximate normal bell shape. Second alternative says that if we again calculate samples of size n that are large enough, calculate the sum of each of those samples, create a histogram, then the resulting histogram will again tend to have a normal bell shape. Okay. The size of the sample n that is required in order to be large enough depends on the original population from which these samples are drawn. If the original population is far from normal, then more observations are needed for sample means or sums to be normal. Sampling is done with replacement. It is often difficult to overstate the importance of the central limit theorem statistical theory. Knowing that data, even if its distribution is not normal, behaves in a predictable way is a powerful tool. Suppose x is a random variable with a distribution that may be known or unknown. Using a subscript that matches the random variable, suppose mu x is the mean of x, sigma x is the standard deviation of x. If you run random samples of size n, then n increases. The random variable uh, x bar, which consists of sample means, tends to be normally distributed, and xn is normally distributed, with the mean of x going here and sigma of x root n. Why are they dividing by root n? Hold on. Central limit theorem for sample mean says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 dice and calculate their means, those means tend to follow a normal distribution. As the sample size increases, the distribution of the means more closely follows the normal distribution. Wait, hold on. Are we dividing this by root n? Sigma x is the standard deviation of x. We divide it by root n, we just get we get rid of the denominator, right? In the formula for the standard deviation. The normal distribution has the same mean as the original distribution and a variance that equals the original variance divided by the sample size. Standard deviation is the square root of variance. So the standard deviation is the sampling distribution of the sampling distribution is the standard deviation of the original distribution divided by the square root of n. Standard deviation is the square root of variance. Okay, this makes sense. Um, so the standard deviation of the sampling distribution is the standard deviation of the original distribution divided by the square root of n. What do they mean by original distribution? The population, you mean? Population distribution, original distribution divided by the square root of n. The variable n is the number of values that are averaged together. Not the number of times the experiment is done. Number of values that are averaged together. Yeah, I don't understand what they're doing here. Sample size increase, the distribution of means more closely follows a normal distribution. Okay. So the mean of the original distribution, standard deviation of the original distribution, which we don't know. Um, Okay, so n is the number of items in our sample. Put it more formally, if you draw random samples of size n, the distribution of the random variable, which consists of sample means, is called the sampling distribution of the mean. Sampling distribution of the mean approaches a normal distribution as n increases. The random variable x mean has different z scores associated with it from that of the random variable x. The mean is the value x bar in one sample. Okay, this is going to bother me. Mu x is the average of both x and x bar. So sigma x, standard deviation of x, is called the standard error of the mean. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n is equal to 25 are drawn randomly from the population. Find the probability that the sample mean is between 85 and 92. Find the probability that the sample mean between 85 and 92. So the sample mean is going to be following this distribution, right? So unknown distribution has mean 90 and standard deviation of 15. So if you're talking about the sample, the standard deviation of the sample, then the standard deviation will be 15 divided by 25, right? Root 25, which is just 5. 15 over 5 is 3. Between 85 and 92. There's a 0.7%. There's a 70% chance that the mean would be inside this area, yeah. Central limit theory for sums. Suppose x is a random variable with a distribution that may be known or unknown. And suppose mu x is the mean of x. Sigma x is the standard deviation of x. You draw random samples of size n, then as n increases, the random variable sigma x consisting of sums tend to be normally distributed, and sigma x is normally distributed with n mu x and sigma x times root n. The central limit theorem for sums says that if we repeatedly draw samples of a given size and calculate the sum of each sample, these sums tend to follow a normal distribution. As sample size increases, the distribution of mean more closely follows the normal distribution. Normal distribution has a mean equal to the original mean multiplied by the sample size and the standard deviation equal to the original standard deviation multiplied by the square root of the sample size. An unknown distribution has a mean of 90 and a standard deviation of 15. Sample of size 80 is drawn randomly from the population. Find the probability that the sum of the 80 values is more than 7,500. So mean is 90, but 90 times it with n, 90 times 80. And then we have standard deviation of 15. 15 times root 80. So the sum of the 80 values is more than 7. Okay. Um, more than, so 0.013. Yep. Find the sum that is 1.5 standard deviation above the mean of the sum. I don't know if it allows Desmos has inverse norm. Wait, let me see. Inverse norm. Inverse normal. What is this inverse CDF? In a recent study, it was reported that the mean age of iPad users is 34. Suppose that the standard deviation is 15 and the sample size is 50. So we have 34 times it by n, which is 50. Standard deviation is 15 times root 50. What is the mean and standard deviation for the sum of the ages of the iPad users? What is the distribution? Okay, this we just need to calculate it. Find the probability that the sum of the ages is between 1500 1800. Zero 0.797. Find the 80th percentile. We have the inverse norm and we get 1789.3. It is important for you to understand when to use the central limit theorem. If you're being asked to find the probability of the mean, use the CLT for the mean. If you're, what's the CLT? Oh, central limit theorem. If you're being asked to find the probability of a sum or total, use the central limit theorem for sums. This applies to percentiles for means and sums. We are being asked to find the probability of an individual value. Do not use CLT. Use distribution of its random variable. The law of large numbers says that if you take samples larger and larger size from any population, then the mean of the sample tends to get closer and closer to mu. From the central limit theorem, we know that as n gets larger and larger, the sample means follow a normal distribution. The larger n gets, the smaller the standard deviation gets. This means the sample mean must be close to the population mean. We can say that mu is the value that the sample mean approach as n gets larger. Central limit theorem illustrates the law of large numbers. I'm feeling a bit sleepy, so I'm going to be rushing through this. Uh, I mean, this is the only last chapter that's left because the other one are exercises. Suppose that a market research analysis for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. The analysis finds that for those people who exceeded the time included in their basic contract, the excess time used follows an exponential distribution with a mean of 22 minutes. Consider a random sample of 80 customers who exceed the time allowance included in their basic cell phone contract. Let X, the excess time used by one individual cell phone customer, exceed his contracted time allowance. Excess time used by one individual cell phone. X follows exponential distribution. Uh, Mu is 22 and sigma is 22. Let the mean, so the mean excess time used by sample of n is equal to 80 customers who exceed their contract time allowance. And this follows a normal distribution. Find the probability that the mean excess time used by the 80 customers in the sample is longer than 20 minutes. It's asking us to find this. 22, 22 over root 80. What did they say? More than 20, right? Zero 0.792. Suppose that one customer who exceeds the time limit for his cell phone contract is randomly selected. Find the probability that this individual customer's excess time is longer than 20 minutes. Or this is distributed exponentially. So, exponential distribution. Well, the cumulative distribution is 1 minus e to the power of minus mx. M over here would be mean of 22, so 1 over 22. This is the cumulative, right? It's getting closer and closer to. So, anyways, um, if we input 20, that is not the answer. I think this is the answer. 0.402. Yeah, 0.4029. Yep. Okay, I will end the stream here because I have to go somewhere. Um, I'm looking at the next pages, they just seem to be exercises, like physical exercises, going out and collecting data. It's not a worked out problem. I mean, it is, but seems like it seems to be something that's done in class. So, anyways, I will read the next chapter in the next stream. And yeah, I will see you guys next time then. Bye.